All right, today we are diving deep into Mycobacterium leprae. Now, for us as microbiologists, this isn't just some historical bug from a textbook. It's a living, modern-day puzzle. It's an absolute masterclass in evolution that seriously challenges some of our most basic principles in the lab.
And that brings us right to the heart of the matter. Think about it. How do you fight a pathogen when you can't even grow it? All our standard procedures, culture plates, broth, susceptibility testing, they're completely useless here. So what do you do when a bacterium just ignores the entire microbiology playbook? Now, just a quick note before we get started. All the information in this explainer comes from a Gemini deep search. If you want to see the full list of references and really dig into the literature yourself, you can find all of that in the accompanying notebook document. Okay, let's get right to the core of this whole problem. The fact that Mycobacterium leprae can't be cultured isn't just some random quirk. It is the direct, logical result of its very strange evolutionary journey. And this one fact has massive consequences for everything that follows. Mycobacterium leprae is what we call an obligate intracellular parasite. And for this bacterium, that's not a lifestyle choice, it's an absolute necessity. Over millions of years, it has literally thrown out huge chunks of its own genome. It's outsourced its entire metabolism to our cells. This total dependency is the fundamental reason you can't just streak it out on a plate. So let's take a closer look at that genome because it's pretty wild. This process of just shedding genes, it's called reductive evolution, has turned Mycobacterium leprae into the ultimate minimalist. In doing so, it has basically broken all the rules for what it means to be a free-living bacterium. And this right here tells the whole story. Just compare it to its famous cousin, Mycobacterium tuberculosis. Sure, the genome is smaller, but that's not the shocking part. The key is the number of functional genes, less than half. The rest of the genome is littered with over 1,100 pseudogenes. They're like genetic fossils, just remnants of pathways it decided it didn't need anymore. So this idea of reductive evolution is the absolute key to understanding this organism. By getting comfortable and adapting to a super stable life inside our cells, Mycobacterium leprae just ditched all the genes it needed to survive in the outside world. And this isn't just some biological curiosity. It explains everything about this pathogen. And here are the consequences laid bare. Total dependence on a host, its status as an obligate intracellular parasite, an incredibly slow replication time. We're talking a doubling time of 12 to 14 days, and the biggest headache for us in the lab, it is completely, utterly uncultivatable. So, if our gold standard, the culture, is off the table, how in the world do we diagnose this thing? How do you go about identifying an enemy you can't even see in the lab? Well, first, the disease is classified clinically because it exists on a spectrum, and that spectrum is defined entirely by the patient's own immune response. On one end, you've got paucibacillary or PB leprosy. That's where a strong Th1 response keeps the number of bacteria really low. On the other end is multibacillary or NB leprosy, where a weak Th2 response lets the bacteria multiply like crazy. This distinction is absolutely critical for both diagnosis and for treatment. So our diagnostic toolkit has to be different. We start with the clinical signs, things like skin lesions that have lost sensation. A slit skin smear can be used to look for acid-fast bacilli under the microscope, but honestly, its sensitivity in those PB cases is pretty poor. Histopathology is really the gold standard for confirming it. But the real game changer for us has been molecular detection, specifically PCR. And to get the best possible sensitivity with PCR, we don't go after a single copy gene. That would be like looking for a needle in a haystack. Instead, we target something called the RLEP repetitive element. Because there are about 36 copies of this thing scattered all over the genome, it massively amplifies our signal, making it way easier to detect the very low number of bugs in paucibacillary disease. But, and this is a really crucial clinical point, even with our most sensitive PCR, you have to be careful. In PB cases, the bacterial load is so low and can be so patchy that a skin biopsy might just miss the organism entirely. So a negative PCR in a patient you strongly suspect has PB leprosy doesn't rule it out. At the end of the day, the diagnosis often still comes down to clinical judgment. Okay, so you have a diagnosis. How do you treat it? Well, the answer is multi-drug therapy, or MDT, and it's been a massive public health victory. But the exact way it's done can vary depending on where you are. Let's just compare the WHO and the Dutch guidelines for adults. For multivacillary leprosy, you can see they're identical, a 12-month course of rifampicin, dapsone, and clofazimine. Simple enough. But for paucibacillary leprosy, this is where it gets interesting. The 2018 WHO guidelines recommend using that same 3-drug regimen for everyone, while the Dutch guidelines stick with the older 2-drug regimen of just rifampicin and dapsone for 6 months. That's a pretty significant difference you'll see in practice. Now, whenever you talk about treatment, you have to talk about resistance. But again, we hit the same wall. How on earth do you test for antibiotic susceptibility in an organism you can't grow? And the simple answer is you don't, at least not in the traditional sense. It's a direct result of that core problem we keep coming back to. No culture means no myci testing. Phenotypic AST is just impossible. So what do? We go straight to the genetic source code. We now know that resistance in Mycobacterium leprae is almost always caused by single nucleotide changes in very specific genes. It's mutations in RPOB for rifampicin, FOLP1 for dapsone, and GYR-A for fluoroquinolones. We can literally read the resistance profile right out of the DNA sequence. And this is the critical take-home message for any clinical microbiologist. You will not find Mycobacterium leprae in the EUCAST tables. There are no clinical breakpoints because there's no standardized phenotypic method. For this pathogen, antimicrobial susceptibility testing is molecular testing. The whole paradigm has shifted from phenotype to genotype. Full stop. All right, let's zoom out one last time and look at public health. How do we stop the spread of a disease that has such a long incubation period and such a unique biology? The cornerstone of prevention here isn't a vaccine. It's simply early diagnosis and starting treatment as fast as possible. Because MDT is so incredibly effective, treating the individual patient is the single most powerful tool we have to protect the entire community. And this slide shows you just how powerful it is. Just think about this number, 72 hours. After only 3 days of treatment, even a patient with the highest bacterial load is generally considered non-infectious. That is incredible, and it's crucial for patient care, for reducing stigma, and for public health. Of course, there are other key strategies. Standard precautions are perfectly fine for patient care in the hospital. Contact tracing is really important for finding any secondary cases early. And we can also offer post-exposure prophylaxis, or PEP. It's a single dose of rifampicin for close contacts, and it's been shown to cut their risk of developing the disease by about 57%. Mycobacterium leprae is such a fascinating case study. It's a testament to how a pathogen's fundamental biology can completely reshape our entire approach, from the diagnostic bench all the way to global public health. It forces us to innovate. We would absolutely love to hear your thoughts and experiences with this unique organism. Go ahead and subscribe to our channel, and please share your questions or your own clinical stories in the comments below.